The speaker is Ivan. Okay. Today the speaker is Ivan Arraut. Thank you very much for coming. It's a pleasure. Currently, he's working at the Universidad de São Joseph in Macau, China. He got his PhD in Osaka, Japan, Osaka University in Japan. So today he's talking about Quantum Yang Baxter Equations, Nambu-Goldstone Theorem, and the black hole information. Okay, so yeah, we can start.
Thank you very much for the introduction. We talk today. My name is Ivan Arraut from Colombia, PhD from Osaka, University of Osaka, supervised by Yutaka Hosotani, particle physicist, but Hideo Kodama in the last year became the high energy accelerator. So, and after a few postdoc positions, one of them GSPS, postdoc fellow in Japan also. And it's a pleasure to be here. Prague, a very beautiful city. I will mention, well, the talk will base some parallels with gravity, sometimes with black hole physics, particularly. But my point is to explain what's the connection between Yang Baxter equations and the Nambu-Goldstone Theorem. For that purpose, of course, you will see issues later subsequently. We will see that I will paint things like this, where you have pair of Nambu-Goldstone bosons and in the general vacuum. Brian, 0, and the exchange of these particles. You will see later. That these 4 triangles correspond to 4 terms in the commutator or the vacuum expectation value. Let's say this corresponds to the vacuum expectation value of the order parameter. Later, I will explain how this situation emerges. But before going to that point, I will explain the motivation. The motivation is that there was a problem it's not precisely a problem. People knew, even Nambu himself knew for a long time, but people studied in different ways, including Murayama, Watanabe, Thomas Browner, Nielsen and Chada in the past, which is the counting of Nambu-Goldstone bosons in non-relativistic systems. What happened is that normally the Nambu-Goldstone theorem suggests that the number of broken symmetries, when the symmetry of a system is spontaneously broken, is equal to the number of Nambu-Goldstone bosons, which is the dimension of the Cosell space and all these kind of issues. But when this is valid in high energy physics, when you go to the non-relativistic case, the relation goes 2 to 1. It means 2 broken generators or 2 broken symmetries will correspond to only one particle, one gapless particle. And even worse, that gapless particle will have a quadratic dispersion relation and nonlinear, which you will expect a linear dispersion relation from a gapless particle. So that was the initial motivation for studying the problem from this perspective. Then subsequently, of course, there are always ways to connect these things with gravity, because in the physics of black holes, we have always this way to do analogies with condensed matter systems and other issues. Then let me explain briefly what is spontaneous symmetry. I think most of you already know, but let's do it this way. We have a potential. We have a system which is described by a Lagrangian. The Lagrangian has kinetic minus potential terms, depending on some felt. And this potential, when you are going to find the equilibrium conditions, of course, you neglect this and you just calculate this. So in ordinary conditions, the potentials could be like this. This is the typical potential. This will be a potential with a quadratic term. And the equilibrium condition is here, stable. It is the most comfortable thing the system might have. Now, when you start to manipulate the free parameters of the system, in some cases, the shape of the potential changes, and then this condition if you put some particles here, let's put it here, you will oscillate around the equilibrium condition. This equilibrium condition will become favorable, and then the system will try to reach a more comfortable condition. An example is if I increase the temperature of this room, people will not lie and everybody will run away. This is a way this is similar to what happened in this because it implies collective behavior. Another issue is ferromagnetics, for example, when all the magnets align in one direction, it happens when you manipulate the three parameters. We will go case by case, and you will see. Then, spontaneous symmetry weakening occurs. Of course, you need higher order terms, for example, a potential of this form, which is square minus 5 to the 4th. You can put any coefficient here if you want, 1/4, 1/2 here if you want. So it comes out that if you calculate this, you have two possible solutions. One is the trivial one, and the other is when it's different from 0. And this different from 0 occurs when m squared is smaller than 0. In that case, manipulating this free parameter gives you a spontaneous symmetry weakening, and the potential becomes the famous Mexican hat here. Then you have many vacuum states with the same energy, and the system has to select one. So now the system initially was here, very comfortable, and it has to decide which vacuum state select. Which vacuum state select it depends on the external perturbation. The external perturbation will tell you if you go to this way, to this way, or this way. An analogy with this is ferromagnet. If you have a ferromagnet here, you have all the magnets initially randomly pointing in an arbitrary direction. So you have an average zero magnetization. But if you decrease the temperature, and there is a moment where the application of a small external magnetic field will align all the magnets in one direction. So in this case, the vacuum state breaks the rotational symmetry when all the magnets align in the same direction. Sorry to hold here. So this is more or less the same case, and we will explore later what is the relevance in gravity. In gravity, we will see, for example, later that, of course, the black holes, when you have a black hole here, with mass, charge, and angular momentum, I will explain why, for example, the Hawking radiation is some kind of mechanism of spontaneous symmetry weakening. So I will explain that subsequently when we reach that point. But initially, I will explain how the Yang Baxter will emerge in this case. So let's go step by step. Now we understand what is spontaneous symmetry weakening. Very important is that, of course, once the system select one vacuum state here, for example, the perturbation same, and the system select this vacuum state breaks some symmetries of the system. But the Lagrangian still satisfies those symmetries. So that's why it's called spontaneous symmetry. But something very important is that there is a quantity called order parameter. In this case, for example, was the magnetization. But in general, the order parameter is a quantity which was 0. The vacuum expectation value was 0 before the phase transition or before the spontaneous symmetry weakening, and is different from 0 after, which is the case of the magnetization. After, when all the magnets align in the same direction, the magnetization is different from 0. Okay? In black holes, we will see later that the other parameter is the particle number operator, which is 0 before the formation of the black hole and non-zero after the formation of the black hole. So I will reach that point subsequently. So being more formal, a little bit more formal, I can follow probably this scenario here. we have a group sample such that if I have a belt or a vacuum, let's assume this vacuum, I operate with the group with some unitary operation, it gives me another vacuum state. But there is a group, a subgroup of the group under which this ground state is still invariant. In such a case, then the Cosella space, the dimension of this Cosella space gives me the number of broken generators, which are the generators of the symmetry, the charges, and this should be equal to the number of Nambu-Goldstone bosons. Gapless particles with a dispersion relation linear, omega proportional to K. And of course, there are ways to demonstrate this theory. The most popular is if you expand here. You expand the potential around the minimum. Of course, you have the first around the minimum. You have the first term. The first derivative term you ignore because around the equilibrium condition will vanish, the derivative of the potential with respect to the field, and the second order terms, which give you, let's put the delta phi square and second derivative term. This is the mass matrix. And of course, the eigenvalues values of this matrix are give us the mass of the Nambu-Goldstone bosons. No? So the theory also is proven if you apply this potential has to be independent. Of course, it has to be symmetric with respect to all the symmetries of the system with respect to this G. Okay? But then when you apply the let's do the transformation. When you apply the transformations of the field, which I will represent this way, zero square. This MB is the matrix here. Executing the transformation under those symmetries, the transformation gives 0. So it comes out, of course, if this doesn't change, it means this will give you a change. Of course, this will be trivial. If the vacuum state doesn't change, this will be trivially 0. But if it changes, it means the symmetry is broken by the wrong state, and then by necessity, all the values of the matrix mass will be 0. Then this is a gapless particle. And the gapless particles, of course, was with linear dispersion relation. But this, of course, this is only high energy physics. As we know, in the case of, in more specific case, for example, in non-relativistic system, what happens in non-relativistic system? We have here, of course, for each broken symmetry, we have one Nambu-Goldstone boson. In non-relativistic system, 2 broken symmetries, 1 Nambu-Goldstone boson. And dispersion relation quadratic. Of course, all the demonstration, I skip the steps, but I think those are in the textbook. I don't have to repeat it so much. And then what's going on? The question here is what's going on?